Okay. So I was asked by Padmanath to talk about this, venerable topics of unitarity, analyticity, and crossing. These are very basic properties of quantum field theories. And the idea, of course, is what is the point of discussing these ideas which have been around for a long time and have been used in the past before we had, for instance, successful theories of the electroweak interactions, electromagnetism, and also the strong interactions. Today we have quantum chromodynamics, which is a theory of quarks and gluons. The properties are very well known, asymptotic freedom, and so on. But then this means that in the low energy sector, where quarks are strongly interacting and are bound inside hadronic states, you can't do very much with the QCD Lagrangian, and then you have to use other techniques to continue to probe the properties of the strong interactions or the residue of the strong interactions, which may be an effective theory. And there may be methods needed to make this theory predictive, where you can't really use perturbation theory. So these properties of unitarity, analyticity, and crossing are always true, whether you like it or not. And it's also manifest in perturbative calculations, Feynman diagrams, and so on, manifestly have these properties. But supposing you don't have a perturbation theory, how can you use this? And how do you use these methods to improve various predictions and contributions of strongly interacting particles? Some of the leading examples being, for instance, the hadronic vacuum polarization contributions to the anomalous magnetic moment of the muon, which is one of the most important experiments that we have in the low energy sector, and also probably to improve determinations of physics in the weak quark sector or in the pion sector, and also ultimately for comparison of results coming from the lattice, which is a method of computing strong interaction properties on the computer and how to make contact with phenomenology. On the other hand, there have been developments in the last 10 or 15 years, which goes under the rubric of bootstrap. There are various kinds of bootstrap. It's a program that also existed in the 60s, a certain kind of bootstrap, what was known as S-matrix theory, which tried to use the general properties of scattering amplitudes and also analytic continuation in angular momentum quantum number, which of course is not rigorously proved or anything like that. So this was needed to try to improve the properties of the strong interactions on the one hand. And today you have conformal bootstrap, you have S-matrix bootstrap. There are hundreds of papers that appear in the archive. Luckily for me, I've stopped reading the archive. So these also have to encode these properties as some kind of a background. A lot of this work goes on the computer of trying to solve all sorts of equations which have to be true and to find their solutions on the computer. So I really don't know what they do. And I was also invited by the EPFL in Lausanne 2 years ago to talk about these topics, and subsequently in Annecy in France in November of 2024. So these are lectures in a sense that I've already given and prior to that gave a small set of lectures at the ICTS in Bangalore. So this is the fourth screening of this, shall we say, serial, if you like. And so what we're going to, the playground for us are the particles which constitute the low energy spectrum of the strong interactions. And this is typically known as the pseudo-scalar octet and consists of states arising from three lightest quarks, the U, D, and S quarks. And these are organized in a plane which is known as the T3 and Y plane, where Y is the strangeness with a minus sign, and T3 is the third component of the isospin, because we study the properties of the strong interaction Hamiltonian, which enjoys a symmetry, which is SU3 cross SU3, left and right. So this is in the limit that the mass of the U, D, and S are all sent to zero. The strong interaction spectrum has the strong interaction Hamiltonian has this symmetry, but this is spontaneously broken by the QCD grounds through the vacuum expectation value of a quark condensate, and this leads to a symmetry that is known as SU3V. But these actually are not equal to zero, but MU, MD, and MS are, they're not zero, but much smaller than a typical hedonic scale, which you may take to be the mass of the nucleon. And the states of interest to us, the pseudoscalar octet consists of the pi minus, the pi 0, and the pi plus, which are not strange states. They have no S quark in them. And there are other states which have the S quark in them. There's 4 of them. One of them is called the K naught. The other is called the K naught bar. And then you have the K plus and the K minus. And these are all made up of QQ bar pairs. And you'll be able to see that this is a US bar. This is an SU bar like that. And then this is a DS bar and a D bar S. D bar S like this. And then there is an 8th partner of this, which is known as the eta, that sits over here. And these particles would have been stable, except for the fact that the weak interactions are also present. And because of the weak interactions, these particles are unstable, and then they decay. But if there were no weak interactions in the universe, they should all be stable. So neither weak interactions that change the flavor of quarks or any kind of flavor changing that happens in the universe is because of the weak interactions. And you should know that the mass of the pi plus, which is one of the lightest, is about 139 MeV, but the pi 0 is a bit lighter at 135 MeV. And we know that the pi 0 decays to 2 photons through the chiral anomaly, and the pi plus, of course, decays into muon primarily, also decays into the electron, and the kaons also decay. And then there's also the mass of the kaon, which is roughly 495 MeV. Okay. So this means that the S quark typically is much heavier, and so that's the way it is. So the pi plus itself would decay. Pi plus decays into mu plus and a neutrino, mu type neutrino, and this is because of the weak interaction with the emission of a virtual W, then decays into mu plus and a mu mu, or into an E plus and a mu E. This, although the muon is heavier, much heavier than the electron, it decays primarily into the muon because of the V minus A structure of the weak interactions, and this is called helicity suppression. And the lifetime of the pion due to this decay is given by 8 pi F pi squared G squared M mu squared M pi times M pi squared by M pi squared minus M mu squared times 1 by VUD squared, where this is the Kobayashi-Maskawa matrix element. And this quantity F pi is known as a pion decay constant, which then later enters into our considerations as far as the strong interaction is concerned. So this is the key thing. Even though a lot of what we'll be talking about is the strong interaction sector, parts of the strong interaction sector actually are measured by the weak interaction. Okay. And what the lattice people try to do is whether you can obtain quantities like this from first principles or not. And these have standard constants such as the Fermi constant, various masses, etc., and is an experimentally determined quantity. And typically, with this normalization, F pi is 0.132 GeV. And very often in the strong interaction sector, we will be writing F pi as F by square root of 2, which is 93.4 GeV. Okay. So this is the background for our trying to understand the strong interactions. And these quantities over here, all these particles lie in this particular plane, which have to do with the representations of this SU3 cross SU3. And these are said to be approximate Goldstone bosons, bosons of spontaneously broken axial vector symmetries. So somebody should have asked me, what is this V that I wrote over here, whereas there's an L and an R sitting over here. So this V here is equal to L plus R, whereas what has vanished is L minus R, which are the axial vector symmetries. Those are spontaneously broken, and Noether's theorem tells you that whenever there's a continuous symmetry that is spontaneously broken, it gives rise to massless particles. In this case, approximate massless particles, which are known as the Goldstone bosons of the spontaneously broken symmetry. Okay, and we know that it must be axial vector symmetries because these are pseudo-scalar particles, by which we mean that the Jp is equal to 0 with a minus sign like that. Okay, so this is the basic particle physics that we need to know in order to discuss what is the topic of these lectures, which is analyticity, unitarity, and crossing. And then we have to be able to establish what are known as dispersion relations for scattering amplitudes, form factors, and other quantities of interest. I'm sorry, I can't hear you. Yeah. Yes. 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 Hey, it's too heavy, no? Yeah. The tau is 1.78 GeV, which is much heavier. Yeah. Right. So it cannot decay. It's not allowed by energy conservation.
From this expression that you have written,
yeah,
yeah, I understand why electron is suffer.
No.
Because if I just look at the
No.
independence of the electron.
No. Yeah, you can't quite do that. It's sitting somewhere else, but it's not here. Yeah.
But there are components coming from the head.
Yeah. Yes.
They basically go into that.
Yes. Yeah. Yeah. No, I don't think you can see there. Maybe it's here. I don't know. Maybe there's also an mu squared over here. So maybe I don't know exactly. I think it's over here. That makes the lifetime much larger to go into the electron. Yeah. But I don't know immediately whether it's right or wrong. Yeah. Yes.
So what exactly is helicity suppression?
Helicity suppression arises from the fact that a spinless particle, namely the pion, is decaying into a pair of spin half particles. Okay, so you're sitting in the rest frame of the pion, and then it decays into a muon in one direction, and the neutrino that's emitted in the opposite direction. The neutrino, and now I'm talking about pi minus. The neutrino is always left-handed. Okay, so because it's always left-handed, because of angular momentum conservation, there are some constraints on how this can happen. You can see pictorially, it's also given in many textbooks, but I don't immediately remember the reason for this.
Also, you mentioned something about broken symmetries given approximately massless particles. So
Yes. No, broken, spontaneously broken exact symmetries, continuous symmetries lead to exactly massless spin zero particles. That's known as the Goldstone theorem in quantum field theory. Here, the symmetry is only approximate. So the resulting Goldstone bosons that you get are not exactly massless, but they are very light on the scale of the hadronic interactions. Yeah.
Will it be possible to calculate exactly the masses that arise from approximately broken form of this equation?
That you have to ask your lattice friends to do it, okay? Because we don't know exactly what is the quark condensate, we don't know exactly what is the quark mass. It's the product of these two that is the square of the pion mass, okay? So one of the goals of the lattice is to actually get a precise number for the condensate, and also you have to tune the quark masses and all these things. But this is at the level of phenomenology, and this was also all done long before we even had QCD or anything. It was just based on symmetries and approximate symmetries. Gell-Mann was the primary force behind it, and people around him who did these things. Yeah. For the lattice people, the pion mass is actually a tunable parameter for most of their purposes. Okay, so the I don't think I'll be able to really write down everything that I have in my notes. I will say a lot of these things in words, and since there'll be a recording, you can follow this. But I also urge you to try to write down these things because I can't write down everything. So the key buzzword is dispersion relations, and dispersion relations is what we need to write down for quantities of interest to us, and it is based on the properties of physical quantities such as form factors and scattering amplitudes when they are viewed as functions of energies, of complex energies, whereas in real physical setting, you have a real energy, you start in the complex plane and then you head to the real axis, and then the relations that you get are these scattering amplitudes or form factors, the real and imaginary parts separately. These are called dispersion relations, and then you express these functions as an integral over the energy line in the physical region over the imaginary part of these quantities. Those are called dispersion relations. The origin of this word is in classical electrodynamics with the Cramer's chronic relation, which all of you know you have studied in your MSc classes, but you're always told that the real and imaginary parts of the refractive index are related to one another because the speed of light is finite. And this is what is known as causality. So these are some of the terms that we will try to understand and try to give some examples to see how such a thing happens. So what does this causality have to do with analyticity? Causality, does this word say something to you? Causality, something causes something, that something follows something as a result of the result of an action. So that is the notion of causality. Okay. So I'm going to give you a simple example that will try to tell you why causality implies analyticity. Okay. So what we will see in quantum field theory, so this is causality and analyticity. So I tried to kind of compress my entire lecture into one page over here. Okay. So those of you who are interested, you can take a picture of this with your Google Pixel cameras. And this is, of course, schematic. And in field theory, which goes under the name of Lyman, Simonzik, and Zimmermann, typically what happens is that the scattering matrix element will have a piece where nothing happens, and another one that involves objects like this, various factors of energy, etc., and various factors 1 by 2 pi cube, and various integrals like this, and exponentials of e to the I, I p, y, p a, let me see, p a, y minus I p b x times various propagator factors kx, ky, etc., and objects that will involve this theta function. I'm just giving you very, very schematic objects like this, various commutators like this, where these commutators are such that they vanish whenever there's a space-like separation, x minus y squared is less than 0, there's a space-like separation. So this is the cornerstone of where scattering amplitudes arise in the LSZ formulation, and also things like this, which go under the name of, somebody has to tell me what is meant by this theta function over here. Everybody here knows what is a theta function? It's a step function, okay? And here's a step function with a y0 minus x0, and this is what you get when you do time ordering of Green's functions, okay? Z is some kind of a renormalization constant. This is all part of the LSZ technology, which is all unnecessary. I'm just trying to activate the fact that you get exponentials of this kind, and you also get theta functions of this kind. Okay. So typically, this is where S matrix elements arise in quantum field theory. Now I'm going to do my simple example to tell you when there are this kind of space-like separation means that something commutator is 0, or when there is a theta function of this kind, then that will imply that the quantity of interest to you will be analytic in the energy.
And PAs or PBs are the initial and final stage.
Yeah. This you just take this as just a motivation for why an object looks like there are exponentials involving the energies, the momenta, as well as this kind of theta functions.
No, I'm just saying then there should be a delta of momenta also.
Yes, this is not a complete expression. This really is far from complete, okay? This is a very schematic expression to tell you that in field theory, that S matrix elements will involve exponents like this, and will also involve this kind of theta functions, equal time commutators. Now I'm going to take a simple example and tell you why these things have to be analytic functions of the variable that is conjugate to these things, okay? So if you have, for instance, a step function like this in the time variable, then that will imply analyticity in the variable that is conjugate to this y0 minus x0, okay? So here the conjugate variable to the x and y will be these momenta, and then you get analytic properties in the variable that is conjugate to this. Was there some other question? Okay. So here is the simple example that I'm going to take. Consider a simple example. Where we look at a function f tilde of p, which is integral minus infinity to infinity e dx e to the I px times f of x. Okay. Now, if f of x equal to 0 for x less than 0, then I can write f of x as theta of x times f of x. Okay. So this is given. So there's an analog of this theta function in this particular simple case. Then this implies that if f tilde of p converges, if p is complex and imaginary p is greater than 0. In other words, this thing is analytic in P. Analytic in P in the upper half plane. In the upper half plane. It just comes from looking at, let's have to look at IPX. And then this is equal to Ix real part of P minus X imaginary part of P. Okay? And for X greater than 0, because of the minus sign over here, minus X times MP is less than 0 if MP is greater than 0. So this is all that I want to prove, and for P belongs to C and MP is greater than 0. Okay. And in field theory, we will find very complicated kinds of commutators and all these things. And therefore, you will have more complicated analytic properties of these functions, but it is a consequence of causality. Okay. So this explains, with a basic example, one of the three terms that have gone into the name of this course: unitarity, analyticity, and crossing. So this is where the analyticity comes from. And it is, of course, a very powerful thing that if a function is analytic, then you can say a lot about its behavior, etc., etc. And it will allow you to establish dispersion relations for the functions of interest to you. All right? So this is, as far as the first term is concerned, analyticity. Now, what's the next term that you would like me to discuss? Is there anybody here? Second, what's the next term that you want me to discuss? From the name of the course. What would you like? There's only two choices. Pick one. Unitarity. Good. Okay. So my friend here in the front row wants me to explain to you all. I think you all know it already, but anyway, since I'm standing here, I think I should explain that. This is a general motivation, but when it comes to a quantity like form factors, which we'll spend a lot of time discussing over here, we will see that a lot of things that will be done to get information on the analytic properties of this thing. So my friend here wants me to explain unitarity. Unitarity. So if you break down the meaning of this word, unitarity, that something has to be equal to 1, right? That's where the word unitarity comes from. So what should be equal to 1 according to you? And what are the objects of interest to us? There's an interaction, there's an initial state, there's a final state. That interaction takes you from the initial state to the final state. And that a given initial state and a given final state, the object is called a matrix element. Okay. So SFI is the matrix element for a transition from a given initial state to a fixed final state. Okay. And in principle, this S matrix has to be something where nothing happens. There's no interaction at all. Given initial state will stay in the same initial state. So it has to be equal to 1 plus something that leads to a transition from one state to a distinct final state. Okay? With the same initial and final states are the same. Obviously, it's the identity that's going to do it. So let's call it IT. Now, unitarity means that things cannot disappear. We must have an overall conservation of things, of particles in the universe, etc. Things may change, of course. You may have, let us say, a pion in the initial state and a muon in the final state, etc. Those are transitions, but things cannot disappear. It means that S dagger F N S N I has to be equal to delta Fi. Okay, so this is the statement of unitarity, that S dagger S is equal to the identity. That's the statement of unitarity. Okay. Yes. Yeah.
What's the reason for this I in this IRT?
You need not, this is a convention, okay?
Okay.
It's always taken with an I,
Oh, okay.
so that you and I both agree on what is the imaginary part and what is the real part, okay? In general, it's a complex object, okay?
Okay.
Yeah, it has a real part and it has an imaginary part. And this is chosen in this particular way in the particular textbook that I have followed, which is Martin and Spearman. And this, I think, is a universally accepted convention, okay?
Okay. Thank you.
Yeah. Yeah, so there are reasons like this why it is chosen that way.
Yeah, I want to say that, yes.
Yeah, thanks. Which comes in the statement that if you plug this into this particular condition, then you get, so plugging this into this, you will get T minus T dagger is equal to I T dagger T, like this. Okay, so you just have to plug it into this condition, and this is what you get. And as you said, since this is admission, this T minus T dagger is going, so this leads to n of Tfi is equal to 1/2 of the sum of T dagger Fn Tfi. So on the right-hand side, you have a sum over all possible intermediate states when you write it like this, where the sum n is over all possible intermediate states which are allowed by all the conservation laws, subject to conservation laws, subject to say global conservation laws, energy momentum conservation, etc., etc. So it doesn't mean that you sum over all sorts of unknown particles at a given energy, only certain particles which are present, those are the ones that will contribute to this particular sum. So let's take an example of scattering problems. Scattering problems, where you have, let us say, scattering of E minus P plus going to E minus I plus. So you have an initial state like this, where you have an E minus pi plus, and then this will give you a pi plus, and then E minus. Okay. So this is one particular scattering process. And you can have, so here, this square of the energy momentum transfer, square of the momentum transfer which is denoted by T, is less than or equal to 0. It's less than or equal to 0. So another process is E plus E minus going to pi plus pi minus, where you have E plus E minus to pi plus pi minus. And this, if this now T is the square of the central mass energy, and T is greater than 4 m pi squared. What we know from experiments is that, so this process is described by what is known as the, so this is known as the form factor for these processes, for these two processes. So here, the form factor F of T, which describes the strength of this coupling, which you cannot calculate from first principles because you don't know how to solve the strong interactions. So this is something that has to be experimentally measured. So in this region, F of T is known to be real. So if you take the complex T plane over here, and then you write down here, so this is the region for pi plus pi minus reduction. And this is the region here for scattering. So various experiments, they measure over here the values of f of t, and it's found to be real. Whereas here, f of t is complex, has both real and imaginary parts. Can someone tell me why this thing must have an imaginary part over here? This is something that you must have come across in your quantum mechanics courses. Why f of t must necessarily have an imaginary part over here? It's because of something that goes under the name of the optical theorem, which tells you that the forward part of the scattering amplitude is related to the total cross section. Okay? So if there is a non-zero total cross section, that E plus E minus does indeed produce pi plus pi minus, it must necessarily have an imaginary part. Okay? And that imaginary part, of course, is of the full process, but this form factor is going to enter it, and that's the reason why it must have a complex part. Whereas here it is known to be real from various experiments, but who tells you that it's the same function f of t that is here? That this could well have been a completely independent process and it has nothing to do with this particular process. Okay? There is nothing which tells you that it's the same function f of t. Of course, its values are different. One of them is real over here and the other one is complex there. So what is the last term missing in this course, in the title of this course? Crossing. So there's this property of crossing which tells you that you could have obtained this process from this process by crossing some of the particles, by taking this pi plus to this side and taking this to this side. Okay, so that is known as the crossing property, where in quantum field theory, it's the same function, of course, evaluated appropriately, that describes two processes that are a priori not related, but they get related by this property of crossing. So it is the property of crossing which tells you that the same function that goes from that relates the value here to the value over here. But there's something more. It is telling you that this thing has to be a very nice function of t when you view it as a complex variable. Okay, although in physical experiments, which is that of scattering, t is obviously real, and for particle production also t is obviously real above 4m pi squared. So this over here, threshold is 4m pi squared. Okay, in physical processes they're always real, but in order for you to go from here to here, you necessarily need to have gone into the complex t plane from over here and then come over here. Okay, so the property of analyticity of the form factor is also somehow built into quantum field theory, but this is a far more complicated, I won't say complicated, it is different from the simple example that we saw. In the simple example, all we could say was that the function has to be analytic in the upper half plane. That's all we could say in that simple example. Whereas for this function f of t, we need to know more about the properties of this particular function. What kind of properties does it have in the complex plane? Okay. You have to go into the full complex plane. And then I've already said that experimentally, you know that this thing over here, it has to become complex, which means that there is a branch cut over here, starting at 4m pi squared and running to infinity. Now, typically, in your complex variable classes, you always are told that if you have two branch points, the branch cut can be chosen to be an arbitrary curve running from one to the other. Here, physically, we are forced to accept that the branch cut actually is the part of the real line that starts at 4m pi squared and goes to infinity. Okay. Yes. Yeah.
Can it be moved at speed with the
Oh, yeah.
Yes. Okay, yeah, sorry. Yeah. Two reactions, you have a T on the top and T on the bottom. Are they both the same T?
It's a S channel, but I've denoted it as T over here.
So the T both get right?
See, I have explicitly written here the square of the momentum transfer. Here I've said square of the center of mass energy, but I've given the name T.
That on the top.
Yeah. Yeah.
We said that we on the second and third quadrants, basically experiments measure this scattering.
Yeah.
And then this is for this top reaction.
Yes.
By E to pi.
Yeah.
And then on the right hand side, what we have branch point and branch is basically.
Yeah.
Section from the zero here, right?
Yeah. Yes.
Now I'm at because since both these are open
There's no problem because this form factor is a function only of one variable. There's no difficulty at all. So it's in the, so that's the whole thing. So you just have, that's why in scattering theory, you always draw a diagram like this, where you have a diagram like this, that this thing is called the S channel and this is called the T channel. Okay. So that's the thing. I mean, this is not as straight, it's not that easy to understand. One needs a little bit of, thinking about it till you get it right. Yeah.
this butter is not the standard for the zero diagram.
Yes.
But measured
Yes. Yeah, right. So when you're doing all this crossing, you have to keep all these things in mind. What is what. Yeah. I mean, here it's relatively easy because these are distinct particles. When you're doing pions and you're having all these isospin labels, it's enough to make your head spin. Yeah. Yes.
So, so as I understand, like, from I1 diagram of complexity.
Yes.
If I take just this was like the constant
Yes.
then the potential will send more of.
That's why there are two diagrams. In Baba scattering, that's why there are two diagrams and you have to take, yeah.
These two diagrams of like a picture.
Yeah, and that's why when you write down the propagators, you make the appropriate changes. Yeah.
So.
Yeah. All this discussion is actually inbuilt into Feynman diagrams. They are manifestly everything. Okay. So this is being done in general where we don't know what is F of t. Here, F of t is not a calculated quantity. It is something that exists in nature, whose properties we now have to find. Okay. Why? Because we don't know how to solve the strong interactions. It's not like I can draw a diagram and then, just say that this is the leading contribution and I can go home. No, in the strong interactions, you don't know what it is. Right. So dispersion relations are essentially that. Yeah. So this F of t, unlike this simple example, is more complicated. And I'm going to suggest to you that it actually is very well behaved. That apart from this branch cut over here, it is analytic everywhere in the first sheet. Okay. So this is a property that I'm going to propose to you because this will be a cornerstone of some of the further calculations that we need to do. Now, crossing is a term that I need to write on the blackboard, that we can go from one to the other. So these are related by crossing. So the ability to relate the form factor measured in this process to the form factor in this is the property of crossing, okay, which in the book of Martin and Spearman, he calls the substitution principle. Not he, but they call the substitution principle, which today we call. Now, Martin and Spearman is, of course, a pretty old book, but it's a fantastic book. I mean, I have rarely come across a book that is so good, okay? I strongly recommend it to you all to learn all these things. Of course, they don't prove everything. It's only, after all, only about 500 pages. So they can't prove everything in 500 pages. take another 4,500 pages to prove the rest. But these properties of f of t, that f of t is analytic in the cut plane cut between 4m pi squared and infinity. Now, it's fairly non-trivial to prove this, and you can read the book by Barton, where all this is proved basically from first principles. It's a very complicated argument, but we have to take this to be true. Okay? So this is for what is known as the pion electromagnetic form factor. So everything that we are talking about f of t here is known as the pion electromagnetic form factor. Why electromagnetic form factor? Because both the E plus E minus and the pi plus pi minus here are both coupling to the virtual photon over here and the virtual photon over here. Okay? So that's the reason why it's called the pion electromagnetic form factor. Those properties, even today, we don't know very well, and it's precisely this quantity that enters into the controversy over the muon G minus 2 experiments, because it's not sufficiently well determined. It's very well determined by many experiments, but those experiments have some inconsistencies amongst each other, and that's the main reason for the theoretical uncertainty that is present even today in the muon G minus 2. There are some other things that I can just mention for general knowledge. There is something known as the Kanazawa-Sugawara theorem. Which tells you that for other processes and other form factors, you may have some isolated poles on the real line, but there'll be no other singularities. Okay, so this has to do with other singularities. If at all. And all this comes from complex analysis. But is this sufficient for us? That we have this cut plane and then we still haven't done anything much with this information. Is there something more that we can do with this information? Well, we did say that there was something called unitarity, and we wrote down this property, but we haven't used this property so far. We want to use this analyticity property, the crossing property, and on top of that, we want to use this unitarity property where there are the sum over intermediate states and so on, to make this thing predictive and to be able to say something about the actual behavior of this form factor. Okay. But there is something nice about a function like this, which is analytic in the cut plane, and there are no other singularities. And that is what I want to get at, because it will tell me something about the imaginary part of this function also. So let me look at the complex plane over here, and let me take a point over here called Z, and then let me take the point Z star over here. Okay. Now, can I say something that will relate the value of the function of f at Z to the value at Z star? Is there any relation between these two? And if so, what would be the relation, or there can be no relation at all? I mean, why should there be any relation after all? These are two distinct points, and why should there be any relation at all? Well, in this particular case, we already have some information about this function, that it has only a cut over here, and that it is real in many parts of the real line. Okay, so our form factor is already known known to be real at least on a segment of the real line. Do you think that this might give us some information over here? That if this function has this very nice property, what would you say about this over here? That this point, how do I get this point from this point with respect to the real line? There's a real line over here, there's a point over here, there's its complex conjugate over here, right? So how do you think you can go from this point to this point? By holding a mirror, right? So this is a reflection of this point, okay? So there is something known as the Schwarz reflection principle. Schwarz reflection principle. Which tells you that f of z is equal to f star at z star if f of z is real on some segment of the real line. Of the real line. Not everywhere, but in a domain containing that segment. But for us, in our case, actually, it's not just a segment of the real line, but all the way from 4n pi squared to minus infinity, we know that the function is real. So this function, so this Schwarz reflection principle is telling you that this thing here is going to respect this property everywhere in the complex plane. Okay. So that's very nice. So what this means is that the value of the function just above the real line and just below the real line, how much will they differ by? So if you take the limit of f of z plus I epsilon minus of f of z minus I epsilon, in the limit epsilon goes to 0, what do you think you should get? I'm going to stop here for the coffee break, or maybe a bit more than this, but so it's in your own interest to tell me as quickly as possible what this particular answer is. Just above and below, what do you think it would be if you take the difference between the two? What do you think you would get? All of you are very shy. You're not going to tell me the answer that you know. So where was I writing? I have lost. Yeah. So you will get 2i times imaginary part of z coming from above. Okay. So this is very nice that the real part of the function here and here is going to be the same as they come closer and closer to each other, but the imaginary parts are just going to be differing only by a minus sign. Okay. And so this is a very useful and important property for the form factor, and it will help us to become more predictive. Okay. So now let me do a little more before we break for coffee and set up what is called a basic dispersion relation for this form factor. So if a function is analytic and I choose a contour f of z naught, it's 2 pi I, and I choose a contour so that I don't cross any singularities, right? This is for z minus z naught dz. Do you all agree that this is true? You all agree that this is true? And why is this true? Well, because Cauchy said so. So this is Cauchy's theorem. Cauchy's theorem. How about we apply it to our form factor? Okay. The only problem is that our form factor, it has a branch cut in a branch point like this, but Let me choose a contour like this, and then this should be true for this function also, as long as this contour is this, right? But let me not choose a contour like this, but rather let me deform this contour. I'm always allowed to deform contours. I take a contour and then I deform it like that. And I'm allowed to do this as long as I don't cross the branch cut, right? So I do this and then I come back like this, right? And the sense is supposed to be anti-clockwise, like so. So this is anti-clockwise, anti-clockwise. Let me see how's my clock doing. My clock is still running behind, so I'm okay, right? So we do this. Do you people like this contour that I've chosen? Is there anybody in this room who likes this contour? All those who like this contour, raise your hands. All those who dislike this contour? All those who are still awake? All those who are still alive? Yeah. Okay, we like this contour. Yes, it's a perfectly good contour. And what is so nice about this contour that I have just chosen? You please tell me, think of all the comments that you and I agreed on before I do this contour about the form factor having nice properties, about it being real analytic, about Schwarz's reflection principle, about my telling you that the imaginary part above the cut is the same with the minus sign below the cut. You like all these things that you agreed upon, right? And I have chosen this particular contour to encode all that discussion that we've been having for the last 45 minutes. That if I now use this as my contour for Cauchy's theorem, then I get a contribution from above the cut and a contribution from below the cut, right? And they are equal to each other because the real parts will cancel and the two imaginary parts will add up because one is the negative of the other. And for the moment, let's assume that this contour that I'm closing at infinity is chosen in such a way that for this function, the contribution from the big arc at infinity is equal to 0. So the only contribution that will survive for this Cauchy's theorem will be a contribution from above the cut minus a contribution from below the cut. And these two are going to add up and you'll get an answer, right? So at the end of all this, you can say that f of t, I'm not going to call it 0, is going to be 1 by pi integral from 4m squared to infinity, imaginary part of f of t prime, dt prime divided by d prime minus t. Okay, so this is the origin of what you will always see in textbooks as a beautiful dispersion relation for the form factor. And the amazing thing about this is that this f of t, t can be a complex number anywhere in the complex plane. And on the left-hand side, it gives you both the real and the imaginary parts of the function. Okay, everything in terms of just the imaginary part of the function along the real axis, right? So the knowledge of the function along the real axis, of course, everywhere along the real axis from 4m pi squared to infinity determines the value of the function everywhere on the complex plane. And we have used the property of the real analyticity, Schwarz's reflection principle, the fact that there is only a branch cut from 4m pi squared to infinity to write down this very beautiful relation. Okay. The only caveat is that we threw away the contribution from infinity. If it was not possible to throw it away, you can dampen the contribution from infinity by a procedure that is known as subtraction. So if it doesn't converge, then you can write this as f at 0 plus 1 by pi 4m pi squared t, imaginary part of f of t prime, divided by t prime times t prime minus t dt prime, like so. So this extra power of t prime is going to kill the contribution from infinity, but the price that we have had to pay is the introduction of an unknown quantity, which is the value of f at 0, which has to be determined from some other source. Okay? So this is an example of a dispersion relation with a subtraction and an unknown subtraction constant. So a lot of work in all this dispersion relation theory goes into determining these unknown subtraction constants and to use things like unitarity and crossing and so on to be able to eliminate these unknown subtraction constants in terms of objects that can otherwise be determined. Okay. So I think I will stop here and then we will pick up from here and do some more fun stuff in the last hour after coffee. Okay, so let's stop now. Okay, so next thing we need to do is to impose this unitarity relation for the form factor. We haven't done it so far. So the question was, what is this form factor that I've been talking about? It's the quantity that enters the actual physical cross section in the relation, in the reaction, E plus E minus goes to pi plus pi minus. It's experimentally measured. The modulus squared is measured. So obviously we don't know what the real and imaginary parts are. We only know the modulus squared. So there is more work we have to do in order to try to extract these things. And this is where perhaps unitarity can come in handy. So we have to look for unitarity relation for form factors. Unitarity for the form factor. And our final state is pi plus pi minus. And our initial state is a state that contains a virtual photon. Never mind the fact that the E plus E minus actually produced this virtual photon. We don't care about that. We'll just say that there's a virtual photon is essentially our initial state. So our imaginary part of f of t then should be the imaginary part of pi plus pi minus t gamma, which is, and the unitarity relation told you that this has to be the sum of all intermediate states of T dagger and like that, and its Hermitian conjugate N T gamma star. Now there's a factor of 2 that has disappeared. I don't know why so. This is a big homework problem for you. What happened to the factor of 2? Because I think these are all like schematic relations. So somewhere some black magic has been done and that factor of 2 has disappeared. So let us look at the elastic region only. Elastic region. So elastic region is the region when T is between 4m squared and 16m squared. What happens at 16m squared? You can have E plus E minus that goes into 4 pions, right? So 4 pion masses squared is 16 m pi squared. So it is no longer elastic above 16 m pi squared, but actually the inelasticity is rather weak. So actually the pion form factor continues to be elastic for a much higher region. Then you will cross one more threshold, which is the kk bar threshold, which is much higher, where you can have E plus E minus going to k plus k minus also. So that's the next higher threshold. So there will be new branch cuts starting at each one of these things. So you have to remember that this f of t, it has many overlapping branch cuts and so on, but doesn't matter. We are for the moment going to confine ourselves to this region where it is elastic. And here the only contribution comes from the 2 pion state where the angular momentum J is equal to 1. Why should the angular momentum state of the pi plus pi minus pair be equal to only 1? We said that whenever we write this unitarity condition, the sum over intermediate states is over all those states that are allowed by the various conservation laws. Okay. So here we know that the angular momentum of the photon is equal to 1. Therefore, the pi plus pi minus state that is produced, which will contribute to the state, can only be one that has the same angular momentum conservation rules and selection rules as allowed. So J equals 1, and this is also something that we will call I equal to 1, where this I here stands for the total isospin of the pi plus pi minus pair. Now remember that in the pseudoscalar octet picture that we drew, we had this I3, and then we had marked the pi 0, pi minus, and a pi plus. Why is that? Because the pions lie in an isotriplet. Okay. So if you have a 2 pion state, then the total allowed values of the isospin are 0, 1, and 2. The rules of combining isospin are exactly those of combining spins. If you have 2 spin 1 particles, the total allowed values of spin are 0, 1, and 2. Isospin, as the name suggests, this was introduced by Heisenberg, is something that looks like an internal spin. That's why he invented the name isospin, because it has the same mathematical properties as that of spin. And Heisenberg introduced this in the context of neutrons and protons. And he said that it's like an isospin half up and isospin half down. Later, when pions were discovered after Heisenberg's first introduction by Yukawa, they were found to be an isospin triplet. Okay? So all these things are well understood. Okay, so then this, yeah. Yes. Yeah, it doesn't matter. Yeah, but we are only talking about this. Yeah. So this thing over here, so imaginary part of f of t then is equal to the scattering amplitude. So this is going to give a scattering amplitude where this intermediate state is going to be a pi plus pi minus state, pi plus pi minus state, pi plus pi minus state with j equals 1, I equals 1. Okay. So this over here this is our form factor. This thing over here. So this is Antoine's question, what on earth is this form factor? It is this matrix element between the pi plus pi minus and the photon state sandwich between the transition matrix element. So this is f of t. And what is this over here? So this is pi plus pi minus going to pi plus pi minus. So this is nothing but the scattering amplitude, but not the arbitrary scattering amplitude, but a scattering amplitude which has this isospin and this spin. So it's actually a partial wave amplitude, but for the moment, let me just write it as t star pi pi of t. Later, we will identify this with something known as the partial wave amplitude. But to just give you pictorially what this is, imaginary part of f of t is imaginary part of this photon going to a pi plus pi minus is equal to, so this is the unitarity relation. So this is pi pi. This is exactly what I've written over here. The right-hand side is the pi pi scattering amplitude multiplied by, if you cut this diagram, this is again the same thing that we have over here. Okay. Notice that this is the same as this, and this is the pi pi scattering amplitude. So this is the diagrammatic representation of this. But later the inelastic, so this is the elastic part. Later you can have the inelastic contributions that come from production of two pions going to two pions. Over here, pi 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 pi. So one of my friends is supposed to be a TA, asking about multi-particle unitarity. Where is he? Yeah. So here you see here's a kind of a contribution of pi pi going to four pions. That thing contribution is also there. Or you can also have a further contribution of, let us say, kk bar over here. Let me give it to the dashed line like this. So this is kk bar, etc. So this is the diagrammatic representation of the inelastic contributions. Okay, so now let me write this down. And this actually ignores some of the other factors that come in over here, and we need some corrections. This is a very schematic expression. And in principle, as somebody also said, that there should be energy momentum conservation and all those things. That will lead to what is known as a phase space integral, and some further factors would also be contributed. So I will write down now the precise unitarity condition, imaginary part of f of t. Now I'm going to write down rho of t, t11 of t, f star of t, theta of t minus 4 m pi squared. So this is known as a partial wave amplitude. How many people here have heard of a partial wave amplitude in relativistic or non-relativistic scattering theory? Have you come across a partial wave amplitude? Doesn't matter. Please tell me if you have or you haven't. How many have? How many have never heard of a partial wave amplitude? Okay. So the scattering amplitude T, which is the probability of any two particles A and B going to C and D, is a function of two variables, the center of mass energy, square of the center of mass energy, and the scattering angle, most of the time taken in the center of mass frame. Okay. So this is the scattering of a particle A, B, going, let's say, to A and B. Okay. And here is the angle theta. This is beam energy E and E, like so. So S is equal to 4E squared. And this is theta. Okay. So this is the probability of AB going to AB. This in the center of mass frame, which is the most convenient frame, is decomposed into a set of amplitudes F, which are a function only of the energy, and something else that should capture the angular dependence. And how would you like to capture the angular dependence? What do you think could be the various functions? Yeah, well, here is a simpler case. So it's just the Legendre polynomials PL of cosine theta. So these are the Legendre polynomials, and this is called a partial wave amplitude. Partial wave amplitude. So obviously FL, I'm sorry, it must necessarily have an index L, which denotes the angular momentum associated with this partial wave, FL of S. Okay? So it's called the partial wave amplitude, and this is called the partial wave decomposition. Okay? And of course, we all know that these Legendre polynomials are a wonderful set of orthogonal polynomials, which are defined between -1 and 1, and then they have orthogonality properties, and they're very nice, a complete basis, and they are all ubiquitous in any scattering problem you'll run into these guys. So, because of conservation of angular momentum, we end up with only one partial wave in this particular unitarity relation because of conservation of angular momentum. And that here, this stands for the isospin, and then this star stands for the angular momentum over here. Okay. And this is a function only of the energy. You don't need the PL of cosine theta, nothing. And this rho of t comes from phase space integral. Rho of t is square root of 1 minus 4 m squared divided by t, which is associated with the integration that you have to do when you do the sum over all intermediate states. Okay. Good. So this is the partial wave amplitude. And in the elastic region, we already said 1 by 2i f of t plus I epsilon minus f of t minus I epsilon is equal to. So now I'm going to use the this thing here and evaluate what this thing over here is equal to 1 by 2i exponential of 2i delta 1 of t minus 1 times f star of t. Okay. Now, how many of you can identify this quantity delta that I have written down over here for you? Have you heard the word? I'm trying to hear from you all. What is this thing called? You know it. Tell me. No, this is the phase shift. You know, in scattering theory, this is the phase shift of the scattering, phase shift. This is not a very familiar form, but there's a more familiar form, and I'll just do algebra for 2 minutes for comic relief and show you what the more familiar form of this elastic unitarity condition looks like. So let's see here. Supposing f11 of t is, as I said, 2i rho of t times exponential of 2i delta 1 of t, close this, minus 1, as I have said. Yes, oops. I think this is wrong. I have to close this. Where did I have to close this? I think it has to be closed here. Yeah, minus 1. Okay, so this is equal to 1 by 2i rho of t times cosine of 2 delta 1 of t plus I sine 2 delta 1 of t minus 1. So this is equal to 1 by 2i rho of t minus 2 sine squared delta 1 of t plus 2i sine of delta 1 of t times cosine of delta 1 of t. So this says that the real part of f11 of t is 1 by rho of t. This form I'm sure many of you have seen in your courses, delta 1 of t times cosine of delta 1 of t, and m of f11 of t is 1 by rho of t sine squared delta 1 of t. And mod of f11 of t squared is 1 by rho of t squared times sine squared delta 1 of t times cosine squared delta 1 of t plus I plus sine squared delta 1 of t, and this is equal to 1 by rho of t m of f11 of t. Have you all seen this particular form of this unitarity relation? You must have, because this is what is used to prove the optical theorem, okay? Wave by wave, if you do and then you add it up, then you get the optical theorem that the imaginary part of the forward cross section is equal to the total cross section. Okay? Of the scattering amplitude is equal to the total cross section. Okay. Now, these are all things which are necessary and useful in order to study these phase shifts and to be able to represent phase shifts. So since we are here, I also want to say a little bit more about a more general way of writing and representing this partial wave. There's a more general way. So this was the elastic way of writing it. Now, if I have to generalize this to an inelastic case, then I'll have to multiply this by a prefactor, which I'll do in this part of the blackboard. So FIL of S is eta IL of S e to the 2I delta IL of S minus 1 divided by 2I rho of S. Have you people come across this before, this eta? This eta is what is known as the elasticity parameter. If it is equal to 1, then you get the elastic case. If it is not equal to 1, obviously, it represents the inelasticity in a reaction. And then there's a very nice way of representing elastic and inelastic reactions and partial waves. And this is done in the Argand plane of 2Q FIL. And this is from Martin and Spearman, by the way, even the great book of Martin and Spearman, definitions sometimes change by some factors here and there. So every single time you have to go back and check what this thing looks like. So in this particular plane, in the elastic case, as the energy changes, this is 2Q times real part of FIL of this, and this is the imaginary part of FIL of S times 2Q. What do you think this thing over here should be? So this thing here has a real squared plus an imaginary squared. This thing here has an imaginary on the right-hand side. Supposing we regroup everything and rewrite this thing. For the elastic case, what do you expect to see in this Argon plane? This will have a real squared plus an imaginary squared, and then there'll be a minus imaginary squared, right? There's a imaginary squared minus an imaginary plus a real squared. So what do you think this thing is going to represent in this Argon plane? No, 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 no. So you have a real and imaginary. It has a quadratic equation. Okay. So what kind of curve do you think it should represent in this plane? It's a second order. It'll be a circle, right? So it'll be an Argon circle as long as it is elastic. So if it was always elastic, then it would start over here and you would get a circle like this. But what happens is if there is an inelasticity that sets in, then this thing will migrate inside this Argon circle. Okay. So this is an Argon circle for the elastic case. And then this is when eta is not equal to 1, it creeps inside. So whenever you see papers on phase shift analysis, you will see that they will always be plotting things on this in this Argon, in the Argon circle like this. However, these things are saying something pretty amazing for us. Okay, this thing over here can also lead to inequalities, and these inequalities are going to say something about the imaginary part. Okay, that the imaginary part has the following behavior, that this so the imaginary part of Fi L of S will always be greater than or equal to rho of S times Fi L of S squared. Now, this is a very profound statement over here. It says that this imaginary part is always positive definite. And in the dispersion relations that we will write, the dispersion relations will always involve the imaginary part. And if you have an integral over an imaginary part that is always positive, then you can say something about the behavior of that function. So this is where the notion of positivity comes from in all these dispersion relation studies, and is one of the hot topics in many, many areas of particle physics, is the use of positivity. It comes from this basic unitarity argument. Okay. There are many books that you can see and read and so on. However, there's a bit of a cheat. I did not tell you why this should be true. Why should this be true? This also comes from imposing unitarity on partial waves and on scattering amplitudes. Comes from imposing unitarity on partial waves. When we imposed unitarity on the form factor, it involved itself and it involved a partial wave. Okay, so this is not a closed system over here, right? Because something involves somebody else, so it's not a closed system where, you know, it's like people are just closing in on each other, whereas this thing is a closed system over here where the real and imaginary parts of the same wave determines itself. Why should this be true? This is true because of the original partial wave expansion that I erased, and because of the orthogonality properties of the Legendre polynomials. Okay, and these are not easy things to prove, but there are these standard textbooks in which all these statements are proved. There's this book by Burckhardt where these statements are also proved. Okay. So I started out talking about all these things because I wanted to do something with this unitarity relation for the form factor. and I want to do something with this so that I can get some information about this imaginary part of this form factor, knowing that it is related to the scattering amplitude through this relation. And that will lead us to yet another very famous result. Okay, so I should not erase everything. I should keep some things and I should erase other things. So let's see, what should I keep and what should I erase? I don't think I need all this. Are you all with me? Is there anybody with me, or I have lost everybody by now? Have I lost everybody? I lost you? Part of you, little bit of you, yeah? As we South Indians say, mostly. When you say most probably, we South Indians say mostly. Mostly, yeah. Okay. So what do I need now? I think I have removed the, no, this is the thing that I needed. I needed this particular thing over here, and let's try to make some progress from here. So this thing, I don't need this row of t. Now let us keep this here, like this. Okay, so I'm now going to return to this thing where I have f of t minus f of t star. Now remember that this is twice the imaginary part with a factor of I, because it is a real analytic function, Schwarz reflection, etc., etc. This is the imaginary part, okay, up to a factor of 2 and so on. Okay, so this now we said is equal to 2I delta 11 of t minus 1 times f star of t. Okay? Does everybody agree with this? Okay. Do you all agree with what I'm saying? This delta 11 is the phase shift that comes from the unitarity relation. Okay. This is the correct unitarity relation, and I was allowed to introduce the phase shift because of the unitarity relation on the partial waves, which we have not proved, but doesn't matter, we will take it to be true. And this is coming from Schwarz reflection principle, that the imaginary part is f of t minus f of t star. This, all that space factor is gone, and this is true. Okay? Agree? There's something that we can cancel on both sides. Shall we cancel something on both sides? This thing here is the same as this, no? So f of t star is gone. So f of t is 2I delta 11 of t times f star of t. Now let me say that f of t is modulus of f of t times e to the I phi of t, where this is the phase of the form factor. So what can I say about phi of t now? Phi of t equal to? Somebody please plug it into this and tell me what I can say about phi of t. Nothing needed. Only delta? Only delta? Who said only delta? You did? You did. Only delta? Not quite. It's definitely delta, but mod k pi. Okay? Yeah. See? Got you. Should not be in a hurry. Right. So this is a very famous result, and this is called the Fermi-Watson theorem. Fermi and Watson. Most of the things in this course are named after Euler, Gauss, and Fermi. So Fermi, so who's Watson? God knows, poor fellow. Watson theorem. Yeah. Yeah, so? Don't know. This is our unknown knowledge. Yeah. So if you say that some function is equal to some other function, it is only modulo k pi. I mean, the phase cannot be determined, right? Because of the e to the 2 pi I is equal to 1. So no, no. You just cannot tell. This is all you can tell. Well, you can, it may turn out that k is equal to 0. Okay. Now can we do something more with this beautiful statement that we have over here? Okay, I'm going to remove this. So I want to go back to this over here. And then I want to say that logarithm of f of t is equal to minus logarithm of f star of t. So I'll say t plus I epsilon and t minus I epsilon. Okay. Nobody will mind if I do this, right? Once again, same old properties of analyticity, cut plane, all these things. The f star means it's below the cut. F means it's above the cut because it's real analytic. And what is this equal to? Somebody help me with this. If I take logarithm of both sides, take this, then what do I get? I should get 2i times pi of t. Okay. Can this always be true? Is it always possible that we can take a logarithm of this irrespective of what is t? Are we always allowed to do this? Logarithm of a function? You can't do it if there is a 0, right? We said that f of t is an analytic function. It has no singularities, but can have a 0. So that's not very nice if it does. So this may not be well defined. It may have some zeros. May have some zeros. So let us say that it has a, since it's an analytic function and all that, and very nicely behaved, must have a finite set of zeros. Somewhere in the complex plane, there would of course be complex conjugate pairs, or it could be on the real line, etc., etc. So I have to find a polynomial p of t with the same zeros, with the same set of zeros. Then what can you say about f of t divided by p of t? What can you say about this particular function? Well, p of t is a polynomial, so it is perfectly wonderful properties. Okay, it doesn't introduce any singularities, branch cuts, nothing. It's just a polynomial. But then what can you say about this quotient p of t, f of t by p of t? It will not have zeros. The zeros of this guy will cancel the zeros of this guy over here. Okay. So then this you will call as omega of t, which is free of zeros. So log of omega of t plus I epsilon minus log of omega t minus I epsilon is equal to log of f of t plus I epsilon minus log of f of t minus I epsilon. Why? Because since p of t is a polynomial, whether you come from above or below, it's going to be equal. So it will not contribute anything to the logarithm. So this will have to be equal. Yeah. This is sufficiently well behaved function. Yeah. which has exactly the same zeros. Supposing the set of zeros of this f are, they are t1, t2, etc., then p of t is t minus t1, t minus t. Just a polynomial like that. You're choosing. If you know where the zeros are. Doesn't matter, they cancel out. That's the nice thing about all these functions, right? No, but in that case, the polynomial will have to raise that by a factor of n. Yeah. Yeah. No, one can keep complicating all these things, but typically in a physical model, you're not expecting to have any such, crazy behavior. Okay. Okay, so then after this, write a dispersion relation. With a subtraction at 0 for log of omega of t, log of omega of 0, plus integral t by pi, integral phi of t prime, divided by t prime minus t, dt prime from 4m squared to infinity. Okay, you're doing this because the imaginary part of this log is only this 2i times phi of t, and then you have to divide it by the I and the 2, and it goes away. And that's the reason why you get this expression. And therefore, omega of t is obtained by exponentiating this, exponential of t by pi, integral 4m squared, infinity, dt prime times phi of t prime divided by t prime. This is another very famous result, and this is known as the omnis solution. Omnis solution. And it says that the form factor is obtained from the phase of the scattering. Okay, so that's the amazing thing. It tells you that not just the phase of the form factor, but the entire form factor, the modulus as well as the phase, are completely determined by the single phase of the scattering amplitude. So this is from Roland Omnis, who's a well-known French physicist who has a good book on quantum mechanics also. And I think everybody at some stage in their career finds the need to write a book on quantum mechanics somehow. So maybe that's a fixed point into which all theoretical physicists flow into sooner or later. And then something is known about the asymptotic behavior of this omega of t, and it goes asymptotically as t to the minus the angle at infinity divided by pi. Okay. So it also predicts the asymptotic behavior. And not only this, it also tells you about the form factor itself, that the form factor goes as t to the n minus phi of infinity by pi, where n is the number of zeros that Shayantan was so perturbed by. So there, it sits here in the prediction for the asymptotic behavior. This omega naught is it's some normalization over there that has gone into this. Yeah. And if f has no zeros, then logarithm of f of t is t times t minus 4 to the 1/2 by pi integral of logarithm of f of t prime dt prime divided by t prime minus 4 t prime minus 4 to the 1/2. Now, this kind of anomalous solution can be checked in one of the tutorials where we will give a model for the partial wave through a well-known parametrization that's known as the Gunaris-Sakurai parametrization for this partial wave. From that parametrization, we will pull out the phase, and then we will saturate this omnis solution, and then we will check the consistency of the solution. So this kind of problems we have discussed with the TAs for this course. The poor fellows may, of course, run away long before all this can be done, but let's hope that they don't. My notes have become yellow colored, almost like turmeric. So thanks to this yellow chalk. However, while all this has stayed relatively abstract, we can probably check some of these results in effective theories to see if some of these properties are holding for calculations of form factors in low energy effective theories, which give concrete expressions for the form factor as well as for the scattering amplitude. Okay. So that is what I'll do next, but maybe I should pause here to see if there are any questions. Is everybody getting tired? People are getting tired. I can do this tomorrow also. Okay. Somebody has to say either yes or no. How many of you are tired? Nobody is tired. Okay, so well, I am, but I can continue. So this bubble that we calculated today in the first class, which you may think has nothing to do with this class, can be used as an example. Okay, so this bubble that we calculated, the thing over here, one of the girls asked me, this doesn't look like anything that I have seen before. I don't know where she is, from Kriya University. There she is. So I said, look, these are all equivalent ways of doing the same thing. Then there's a finite part of it. There's a loop integral that shows up, etc. And then that loop integral, which I'll derive tomorrow, is something that looks like this. So this is a loop integral like this. And then, so this has a finite part, this loop integral, which we will see tomorrow, which shows up after we do the epsilon expansion thing. When we did the derivation this morning, we had this Gauss hypergeometric function of various parameters and x, where x was p squared by 4n squared. All very nice, but it didn't look like anything that's familiar because it was still in arbitrary dimensions. If you do the epsilon expansion of that expression, you'll get back the familiar finite part of the one loop integral. And that familiar part of the integral is something that looks like this. It's a 16 pi squared times j bar of s is equal to sigma of s times logarithm of sigma of s minus 1, sigma of s plus 1 plus 2, like this, where sigma is again the same phase space factor that I had a few minutes ago, 1 minus 4n squared by s. And the imaginary part of this j bar of s is 1 by 16 pi times sigma of s. And the onset of the imaginary part is only when this p squared or s exceeds 4m squared. Why 4m squared? Because this is an equal mass bubble, and because of the optical theorem, it will pick up an imaginary part only when this p squared exceeds the threshold for the two particle threshold. Okay, and so this is the kind of equation that we will need to justify this for the expressions that we get in effective field theories. I'm going to write down some results for you for what these form factors look like. This electromagnetic form factor is going to look like this. Some of these are actually very, very complicated, but I'll try to do a simpler version than the electromagnetic form factor. There's something known as the scalar form factor of the pion, which at one loop has an expression that looks like this. Gamma bar of S is 1. So this is the normalization at tree level of the scalar form factor. And then it receives some contributions from the effective Lagrangian at higher orders. And these are what are called the low energy constants of chiral perturbation theory, which contribute to this form factor. But this is not the part that is interesting to us. But more interesting is 2s minus m pi squared divided by 2 pi f pi squared times j bar of s. Now, your unitarity told you that for s greater than 4 m pi squared, there has to be an imaginary part of this form factor, right? This thing over here should develop a imaginary part when s exceeds 4 m pi squared. Can this 1 ever become imaginary? No, because 1 is a real number. This thing over here is real. S is just the square of the energy. It's a real number, so it cannot generate any imaginary part. So where can the imaginary part come from? It can only come from this expression over here, where there is this j bar of s. And we just wrote that this imaginary part of j bar of s begins when s is greater than 4 m pi squared. Okay? So the imaginary part is going to arise from this. Now remember that the imaginary part of the form factor through unitarity should contain a piece that is proportional to the form factor itself and a piece that is proportional to the scattering amplitude, the partial wave of the scattering amplitude. So this thing over here should be the scattering amplitude of the partial wave, and this is the form factor itself, but evaluated at a lower order in the loop expansion. So this is computed at one loop order. This thing here is a partial wave at tree level, and this over here should also be the imaginary part is generated by the j bar, and then there's a small contribution that comes from the tree contribution of the scalar form factor. So the question is, what is this 2s minus 4 m pi squared, and where is this coming from? Is this a partial wave or not? That is the question. Okay. So I'm going to do a little bit of algebra just to cheer you all up before we leave for the day. Okay. Is that all right? That I do a little more work for about 10 minutes? Is that okay? Okay. 10 more minutes? She's okay. Yeah. Okay. So pi scattering. Pi scattering. Pi goes to pi. How many pi's are there? How many pions are there? He knows. Tell me. 4. Now I have to name one after you. So I know only 3 of them. Yeah. Pi plus pi minus and pi 0. But I prefer to name them in isospin basis rather than in the charge basis. Pi plus pi minus pi 0 are in the charge basis. But let's do it in the isospin basis. And they are, of course, related to each other. So pi scattering is pi A, pi B goes to pi C, pi D. And the most general S matrix element is written as a function A of STU, where we must have isospin conservation. It's called delta AB, delta CD, like this. So this is known as scattering in the S channel plus a scattering delta AC, delta BD, a TUS, and finally delta AD, delta BC AUST, like this. Okay. So your delta has finally appeared now. Not Dirac, but Kronecker. It's a little simpler. Yeah. So this is a very generic way of describing all of pi scattering. But what we do actually is not in this basis, but yet another basis, which is called scattering in definite isospin in the S channel, definite isospin in the S channel. Now, this has a momentum, call it P1, P2, P3, and P4. And for this scattering, I have to say S is equal to, somebody tell me, what are the various kinematic invariants associated with scattering of this kind? So, S is P1 plus P2 squared. Let me take all of them as incoming. P as P1 plus P3 squared, and U as P1 plus P4 squared, with the constraint that S plus T plus U is equal to sum of the squares of the masses, in this case, is 4m pi squared. Okay. Now, given this, there are amplitudes of definite isospin in the S channel, which are defined as T0. What are the various possibilities for isospin that we have when we have three? 0, 1, and 2, right? Because we are combining spin 1 particles. To get total isospin, you can only get 0, 1, and 2. And this, it turns out, this T times ASTU plus ATUS plus AUST. T1 is ATUS minus AUST. Now, when you project these onto partial waves, that's how you get the partial wave amplitudes, F11, etc., etc. Finally, what should T2 be? It is ATUS plus AUST. There's a particular combination which is very interesting, T0 plus 2T2. Can somebody evaluate this for me very quickly and divide this by 3? And tell me what is this combination, T0 plus 2T2 divided by 3? It's totally symmetric. It's a very special amplitude, ASTU plus AUST plus AUS. But this thing also has a property that ASTU is ATUS. This is actually a feature of the fact that pions are bosons. Okay, very good. Yeah. Which one? Yeah, no, yeah. Those denote the states in the isospin basis. Okay. I don't know offhand exactly what these relations are. I don't want to say anything wrong. Yeah. So these factors 3, 1, 1, all these things come from coupling various isospin bases. Okay. How do you couple various spins? J1, J2, when you couple J1 and J2 to get total J in your coursework, what did you have to calculate in order to couple various spins? Now, you people are a little senior. Let me ask the younger people. Yeah. Krebs-Gordon coefficients. Okay. That is one example. But if you want to do more complicated coupling of angular momenta, these are named after Wigner. They're called the Wigner 6J symbols or the Wigner 9J symbols. Okay. So these factors of 3, 1, 1, all these things comes from coupling of these isospins to intermediate states of definite isospin and then to get a definite final state. When you do all those things, these Wigner's 6 or 9J symbols give you all these things. Okay. Now, having done this, now let us try to see where this thing is coming from. Now, Weinberg gave a very nice expression for ASTU in what is known as current algebra, which is again what we were talking about right at the beginning of this course, which was the pseudoscalar octet and all these things, and underlying symmetry is Goldstone bosons. Somebody asked me a question about Goldstone bosons, etc. So Weinberg gave a very beautiful expression for ASTU in current algebra, which was just S minus m pi squared divided by f pi squared. Okay. Now I need one of you to compute this object for me from that expression. I need a volunteer to come up to the blackboard and compute for me T0 from this particular thing. Okay. Any volunteers? One of my TAs. How about you? You look like a volunteer. You. She's just looking like I'm not talking to her. Now, since you're my student, you have to come. Come into it. Yeah, why not? I mean, it has to be a little bit of fun for me also, no? Not just for you all, no? Watching me stand up here and talking. Or you want to come and help your friend, you would do that. She's capable. Okay, very good. Yeah. Yeah. Okay. Forget about the f pi squared. Just do that 3 ASTU. Let's forget about this f pi squared. You need 3 times AS. 3 times this. 3 times this. Open a bracket. No, open a bracket here and write S minus m pi squared. Yeah, plus what's next? You see over there what's written over there. Yeah, so please come and write that. No, so substitute A of T, right? So just open a bracket and write, yeah, T minus m pi squared. What's the last term? Very good, excellent, yeah. Now expand it out. Yeah. Very good. And now S plus T plus U is? So write this as 2S plus S. Yeah. And that is equal to? Very good. So? And what do you have over there? Right. So it agrees. So you have proved the result. She has proved the result that this 2S minus m pi squared appears from the pi scattering amplitude. Thank you very much. Okay. So we have shown now that the unitarity relation is for the form factor is satisfied by the chiral expansion for this using the tree level amplitudes, because we already know that this J bar of S has the right imaginary part. Okay. So I think that this is a reasonable place to start, to stop, and we can pick up from here tomorrow and go on, and it'll be a fair amount of hard work from here also. I think I've covered a fair amount of ground, but I may have to repeat some of these things as we go along, okay? Are there any questions, urgent questions for today, or we can discuss them tomorrow also? How about the boss? Satisfied? Yeah.
There are more. Back to that.